Hi, my name is Neil, and today I'd like to talk to you about the action potential. Okay, so before you get into the action potential, we first have to understand the resting membrane potential. Okay, this is going to give us great insight into the action potential later. Okay, so I'd like to give a brief overview of the factors that contribute. Okay, that create this resting membrane potential, they make it what it is. Okay, so that would be the electrochemical gradient, the equilibrium potentials of the ions, the ion permeability, and the sodium-potassium pump. Okay, so let's go ahead and look at this diagram. I think it'll allow us to see how these factors influence the membrane potential, the resting membrane potential, and give us a good understanding. Okay, so as you might notice here in the top part of this diagram, you'll see that the resting membrane potential is roughly around negative 73 millivolts in a typical neuron. Okay, so our question is how? How is that the case? Why is that the case? Okay, so a place we might want to start is with the equilibrium potentials, right? So we've got the equilibrium potentials for all of the ions involved inside of the neuron, and we might say that, okay, well, we'd probably have these ions diffuse down their concentration gradients until the electrical gradient counterbalances that force. And all of these ions maybe would be doing that at the same time with the same ease. Okay, that's not the case. Okay, so the permeability is different depending on which ion we're talking about. So the resting membrane potential depends greatly on which ions are permeable and which aren't. So as it turns out, potassium here is very permeable to the membrane. It has a great ease in which it can pass through compared to the other ions. So what that tells us, okay, about the equilibrium potential is that it should be around negative 90. Now, negative 73 is close, but it's not quite 90. Okay, well, why is that the case? Okay, so the reason there's a difference is because you see these channels here in gray are called leaky channels. Okay, so what they do is they are always open. Okay, and potassium can pass through at any time. The thing is, there are also leaky channels for sodium and chloride. So these guys are also able to, pass through the membrane, not necessarily with the same amount of ease, but they are also still able to get through. And so sodium here, for example, has a positive charge, right? So it's coming in, right? There's an influx of sodium in the membrane, okay, through the membrane, and that's actually going to raise our potential a bit, which is why it's a little bit different compared to this equilibrium potential, right? Because there are other ions at play here. It's just most of the equilibrium, most of the membrane potential comes from the equilibrium potential of potassium. However, there's one last factor we have to talk about, and that is the sodium-potassium pump. Okay, so this guy contributes to the resting potential in two ways. One, he helps to establish the concentration gradients, okay, of potassium and sodium. So what that means is that those two ions in particular are really the most important for calculating the resting membrane potential because they're actively being maintained by this pump. The second way it's important is that if you'll notice, there are 2 potassium ions going in for every 3 sodium ions out. Now, if you did your math right, there's 1 positive ion missing, right? So we're losing a positive ion every time this thing pumps. So we're getting more negative. And as it turns out, that actually contributes roughly negative 6 millivolts to the resting membrane potential, okay? And the reason that is, that was found through the Goldman equation, okay? So lastly here, we can see how these all come together in the actual calculation of the resting membrane potential because we can see that all of these are components, are terms in this equation. We've got the permeability here represented by P. We've got R, which is the ratio of the transport from the pump. And of course, you've got the concentrations and so on. And it's only of potassium and sodium because of how strongly the concentration gradients are maintained by that pump, okay? So that is how the resting membrane potential is calculated and found. I hope that helps our understanding. Okay, so now that we have a good understanding of the resting membrane potential, now we're going to talk about the phases of the action potential. okay? So before we do that, we're gonna have a quick overview of the action potential phases, okay? So we've got the resting phase, the threshold, you've got depolarization, repolarization, hyperpolarization, go back to resting, and then there are two notions we should talk about called the absolute and relative refractory periods, okay? So here is a little diagram that showcases the action potential, right? The changes in the membrane voltage as a action potential is fired, okay? So if you'll note, we start here, okay, which is the resting membrane potential, right? And we said earlier that that's around negative 70 millivolts, okay? And so what will happen is neurons will receive stimulus, right, in the form of EPSPs, or excitatory postsynaptic potentials, and that will, over time, if they summate enough and hit this threshold of negative 55, the action potential will fire, okay? So that's what the threshold is. Now, once that threshold is met, what will happen is voltage-gated sodium channels will open, okay? They will activate. And when that happens, if we think back to our resting membrane potential, sodium is going to want to rush in, right? Because there's a lot more of it outside, okay? Outside of the cell than there is inside. So there's a large driving force on that sodium. So when that happens, it's going to drive the voltage of the membrane up to like positive 40, okay? So also, one thing that also happens when the threshold is met is delayed rectifiers sort of get put into motion. And what those are a type of a type of channel that opens a little bit after a stimulus is met, okay? So once that threshold is hit, these delayed rectifiers, okay, these channels are going to open. And while they're important, is because once we get to the sort of peak here, that's when around 1-ish milliseconds later, the delayed rectifiers, or as they might be known as, voltage-gated potassium channels open. So when that happens, potassium is going to rush out of the cell, right? Because it's concentrated inside, as we said earlier. So it's going to shoot down, it's going to repolarize, right? Going to get negative again, negative, negative, and negative. However, because there are more voltage-gated calcium channels open, what's going to happen is it's actually going to overshoot the resting membrane potential, okay? And as those, both of those voltage-gated and those the voltage-gated calcium and sodium channels start to inactivate, we'll slowly get back to resting. So the last notion I need to talk about is the absolute refractory period and the relative. So the absolute refractory period is when the sodium channels, the voltage-gated sodium channels, are not able to fire. They've been inactivated, okay? And then once those reactivate, or beginning to recover, but the voltage-gated calcium channels are still open, that's the relative refractory period. So an action potential can still happen here, but it's just going to take a bit more energy than normal, the normal threshold, okay? So all in all, this is the phases of the action potential. Okay, so now I'm going to talk about the current and conductance of sodium and potassium during the action potential, okay? So let's go ahead and start off by talking about current of sodium and potassium. Okay, we're starting with current. So let's first look at figure A here, and the most important thing we want to look at is the early current and the late current, okay? What are those? Well, let's take a look at figure C first and look at the early current. If we look at it, we can see that there's an immediate increase in current, right? That is followed by a change in the direction about 1 millisecond in, and then it slowly starts to approach zero again. So this is reflective of the inward sodium current, okay? And that makes sense based on our understanding of voltage-gated sodium channels, right? So those open immediately, right? Their time course is immediately they activate, and then they start deactivating as the voltage starts to decrease when the delayed rectifiers or voltage-gated potassium channels open, okay? So that's why we see that change in direction around 1 millisecond in, because that's when the potassium channels will start to open. Okay, so early current is the inward sodium current. Let's talk about the late current now. The late current is called the late current because it's a little bit delayed, right? It's a little bit late to start. And as we can see, like maybe roughly around one millisecond here, there's a rapid, not a rapid, but it starts to increase slowly but surely. And this is reflective of the outward potassium current. If we think about it, it makes sense because the inward, the voltage gated potassium channels open roughly about 1 millisecond after the sodium channels open. Okay, so the conductance and current are very similar. They're directly related. So the graphs are going to look very similar here, right? We have that immediate increase for the sodium conductance, and then the sort of slower sort of increase for the potassium conductance. The takeaway here is that they have the same sort of pattern, and that makes sense. Even though they're different, right? Conductance is the ease by which a ion can pass through the membrane. Current is the actual flow of those ions through. They do actually sort of go together, if you will, part and parcel. Okay, so lastly, I'd like to talk about the time course of activation and activation. The takeaway from these graphs is essentially the following. Okay, for sodium, the voltage-gated channels activate immediately, and then a couple milliseconds after, once after the potassium channels have had a chance to lower the sort of start to depolarize the membrane, they close again. Okay, and then for the potassium, voltage-gated potassium channels, they activate about 1 millisecond after the voltage-gated sodium channels activate, and then they inactivate as the member potential starts to get back to resting. Okay, the resting member potential. So lastly, I do want to talk about the propagation of action potentials. So the essence of this is as follows. Okay, this is the axon. As when there's a stimulus that is equal to or greater than the threshold, sodium is going to rush in. Okay, when that happens, we get a bunch of positive charge here in the middle of the axon, which will actually start to depolarize neighboring voltage-gated sodium channels, and this process will repeat, thus propagating the action potential down the axon. Now, in myelinated neurons, this is called saltatory conduction. Okay, and the reason for that is as follows. Myelination actually changes up this process a little bit. It's still, the crux is the same, but what's really happening here is these nodes are generating or having the action potentials with the sodium in flux, and the myelin is actually just helping it move. It's increasing the conduction velocity. It's not actually generating action potentials there. So that'll actually increase the speed if there is myelin, which brings me to my next point. What are the factors that affect propagation speed? Well, myelination, for one, right? It has a better conductance with these on, higher conductance around the axon, so the conduction velocity is greater. The axon diameter also helps, right? So what that is essentially, imagine you have a wide pipe and a really thin pipe, right? There's a lot less resistance for the water flowing through the big pipe than there is for the little one. You can get more current through the bigger pipe, right? Lastly is the internode distance. Now that is the distance between the nodes of Ranvier, which is where those action potentials are generated, right, or propagated. If there are less of them, less nodes between two distances rather than more, the conduction velocity will increase, right, because it has less breaks to take before it gets to the next neuron. That is my presentation. Thank you so much for listening.